Welcome to Crosstalk Solutions. My name's Chris, and this is Solar Powered Wi-Fi Part 3. I'm here with Brandon Yarbrough. He is Crosstalk's wireless ISP expert, and he has also done a lot of work with solar panel setups, including the work that we did for the TV show Castaways in Indonesia, where all you had to power everything was solar, right?
Absolutely. It was 100% solar powered for the entire 7 miles of beach.
In the previous two videos, I was really trying to increase the efficiency of the output or what we could capture with the sun out here in Oregon, where I don't get a ton of sun to begin with, but really just trying to capture the efficiency and seeing how long I could power up a nano station that's receiving a signal and shooting a camera that's also powered by the solar over to my NVR system, and how long can we keep that running. In this video, in Solar Powered Wi-Fi Part 3, we're going to be trying to further increase efficiency by doing a bunch of things, including a brand new solar panel. And on top of that, we're going to be making the setup more permanent, because one of the things that I found in between, the year that it's been since I did Solar Powered Part 2 is that this stuff gets weathered pretty easily. So if you don't have good weatherproofing on the components, you're gonna ruin some stuff, which I did over the past year, and we'll talk about that in a second. Okay, so when I say we're making it more permanent, the first thing is that you can see, I don't know if it's on camera, but I will put up a video. We put up a 8-foot pole and we cemented it into the ground at a location where it should get probably 6 to 8 hours of sunlight on a sunny day here on the Oregon coast. In addition, we're going to be mounting the solar up high, so I have a mounting kit to put the solar right on the pole. It's a pole mount kit that allows us to angle the solar at the in the best way. But first, let's talk about the equipment. So I'm talking about this new solar panel, and what we have here is the Renogy 100 watt 12 volt monocrystalline solar panel. Now you can see this is my old one over here behind Brandon. Now, this one is much smaller than the old one. It's way lighter than the old one. And this panel over here was from Harbor Freight, so it's a piece of junk to begin with, and it was only 45 watts. One of the tests here is with the monocrystalline, the sort of better quality panel. It's 100 watts. How much of that 100 watts are we actually going to get out of the system? And certainly, is it going to stand up to the weather out here over the winter? And will it power this camera and nano station? How long will it keep it powered? It should, in theory, keep the battery charged up a lot longer, because more power is hitting the solar panel, more power is being thrown into the battery, so the battery should be kept fuller longer, yeah?
Absolutely. This panel should be capable of powering those two devices indefinitely with 24 hours of standby.
Yeah. Now, when you were in Indonesia doing those setups, your typical setup was one solar panel that was powering a nano station and a mesh access point, right? That are sort of for the main hub.
So every between 5 and 6 stations, we would put a nano station with a Unify mesh, but most of them were just a Unify mesh station.
And you were powering one Unify mesh access point with what wattage of solar panel?
Those were 50 watt solar panels. However, going back, I probably would have increased that to a 75 or 100 watt just to be safe, because we did have some outages during the monsoons that they were having at the time.
And how much or how many hours on average direct sunlight do you think you were getting on those 50 watt panels?
Direct sunlight, we were anticipating 12 hours because we were right at the equator, but because of the foliage blocking it, I would say we were getting only 3 to 4 hours of direct sunlight, and then obstructed sunlight with 50% coverage the rest of those 12 hours.
Wow. Okay. And you guys, if you want to see more details about that Castaways setup, I will put a link to the Castaways live stream that we did, where we talked all about it. We did a slideshow and all sorts of fun questions from the viewers. Okay, so that is the Renogy 100 watt solar panel that we're going to be testing out here. We also have this pole mount kit. Okay, so the Renogy pole mount kit is $79.99. Yeah, $79.99. And this is good for a single 50 watt or 100 watt Renogy solar panel. It is meant to go on a pole. It has all the mounting hardware you need to put it on a pole. And they also make a double panel version of the same thing. It's a little bit more expensive, but you can put 2 solar panels on a pole mount with this pole mount kit. We're going to go with the same charge controller Victron Energy Blue Solar 7515 MPPT charge controller that I used last year. The charge controller itself seems to be working just fine, but sitting out in the weather in a box that was not weatherproof for the past year and all winter, the Bluetooth dongle appears to have now failed. So this Bluetooth dongle, I have ordered another one, but it's important to have the Bluetooth dongle because this is how I can see the output of the solar panel and when it's charging the batteries, and it gives me, you know, nice graphs so I can see when it's working and when it's not. And unfortunately, this is a $50 part that died over the past year because I didn't have it in a nice weatherproofed enclosure. So that is trash, unfortunately. To fix that problem, we're going with this Altelix. This is a 14-inch by 11-inch by 5-inch pole mount polycarbonate plus ABS NEMA rated enclosure. Okay, so this has different little screw mounting points. It has a grounding spot here so you can ground out your components directly inside the box. And basically you can kind of screw your stuff in here in any configuration. It's also fully weatherproof and it locks. And again, they make these in all different sizes. I ended up with the one that's 14 inches by 11 inches by 5 inches. It's probably a little bit bigger than I actually need, but I wanted extra space in case I decide to put in a network switch at some point. We're not going to do a network switch right off the bat because I don't think we're going to need it. I mean, we have the nano station and you can just power the one camera off the nano station, yeah?
Yeah, well, in this case, we're going to power the nano station and camera off of the nano station's pass-through port, but we could also use the nano switch if we needed additional ports off of that.
Yeah, so I have basically a big enough box that I can expand this setup if I need to. And again, all the pole mounting hardware comes in this box. And you guys will see when we set it up too, the battery does not go in here. The battery is in a separate battery box that for now, I'm just gonna keep on the ground. I will think about maybe getting another NEMA enclosure for the battery as well, but you know, we'll see how it works out.
Yeah, the current battery box is configured with the proper vents, so I don't anticipate needing to move it off the ground. If it does flood in the area, that would be the only reason I would anticipate needing to move it off the ground.
Yeah,
we could possibly get a shelf or something like that to place it on.
Yeah, I mean, that's the thing is for me, it's the box is fine, but it's the aesthetics of having it, you know, sitting on the ground versus actually mounted on the pole. For grounding, right behind Brandon here, we have this is a Skywalker 4-foot copper grounding rod. It comes with the little screw that you need to actually ground things to this. And this drives about 3.5 feet into the ground. What do you think about this? This is capable of grounding the equipment that we're putting up?
Absolutely. We're just going to be grounding the camera and the
nano station.
Nano station. Thank you.
Yeah.
To make sure that everything is grounded properly for lightning protection. The Ethernet surge protector is what actually gets grounded.
Yeah, so we'll be tossing in an ETH SP from Ubiquiti to basically connect over to this ground rod here. And then finally, for our cabling, I purchased some Cat 6 waterproof outdoor direct burial cable. It's nothing special, I'll put a link to it down below, but it was about 80 bucks for a 500-foot spool of that cable. I guess the next step is to just start putting all this stuff together and get the solar panels up on the pole, and let's go ahead and get started.
Alright, so we just finished installing everything, and I'm going to take you guys through a quick tour of what we actually did. So, as you can see up here, this is how we got the PV mounted. It comes down through the blocks into the MC4 connectors, follows the wire down and into our charge controller. As you can see here, it's actually pumping out just under 20 volts at the moment due to the fact that it's not very sunny today. On a typical sunny day, you should see about 22 volts coming out of a 12 volt solar panel. Out of the charge controller, it comes down this wire into our battery box, and it also comes off of the load side, comes into our boost transformer, into our gigabit PoE injector. So out of the charge controller, we're putting 12 volts or 13.75 volts into this boost transformer. So that's boosting our voltage from 12 volts to 24 volts. If we take our pins here, you can actually see it's putting out 24 volts right on the nose. This is how we're powering up our PoE to provide power to the back of our nano station at the moment. When it comes out of the gigabit PoE injector, we can step around to the other side. We're actually going into our Ethernet surge protector here, which is fully grounded, not only through the pole, but we also ran a ground wire into our ground rod, which we drove into the ground, out of the Ethernet surge protector into the main port of the nano station.
You should see a link light here soon. Might take a second.
There it goes.
There it goes. Boom. All right, so what do you think of the setup in general?
It actually looks really clean. This box was just perfect sized for what we were looking to do with it. If you're wanting to put any sort of inverter or anything like that, you're going to need a slightly larger box in order to be able to provide 110 volt. When you start changing your voltages from AC to DC, you really lose a lot of efficiency. And the whole design around this is to keep the efficiency as best as possible, so we're not losing a lot of voltage.
And then what about the size of the pole?
In most cases, I probably would have gone a little bit bigger. It is a little wobbly. The mount itself was designed for a 3-inch pipe. We didn't have a 3-inch pipe, so we used what we had and had to put a little bit of a spacer behind the bracket in order for the U-bolts to seat properly. Also, throughout the entire system, everything is fully fuse protected into the MPPT controller from the solar panel. So we have a fuse coming off of the load side and battery side. Everything is fully fuse protected. The fuse for the battery is right at the battery box. Right now this is a 35 amp hour 12 volt deep cycle battery, and that should be able to continuously power everything given the 100 watt solar panel.
Okay, so I've been running this setup for about a month now, and everything's been working absolutely flawlessly. The nano station, I've been monitoring it with UNMS. It hasn't dropped even a single time. It's been perfectly solid. Now, granted, we're in the summertime, but there have been a number of overcast days, and so what I'm going to do next is I'm going to download the data from the charge controller via the Bluetooth module into my phone. We're going to get the latest data. That's in CSV format. Then we can look at it in a spreadsheet and see how much time is spent charging the battery versus how much time is spent in what's called float mode, where the battery is full and the solar is just being used to top off the battery as needed. Okay, so let's take a look at that next. Okay, so the first thing we have here is a spreadsheet of about 10 days after we first installed everything. So I wanted you to see the consumption versus the yield. You can see that down here, we'll look at the yield. It was pushing between 10 and 20 kilowatt hours with the old solar power, the old solar panel setup. That was the old Harbor Freight piece of junk, the 45 watt solar panel. I was able to get between 10 to 20 watt hours per day out of that device. Then we had some mix up in here. This is when we were actually transitioning to the new one. And then up here, this is where it stayed solid, where we can see that our new watt hours with the new solar panel is somewhere between 60 and 70 watt hours per day. Also, caveat here, I am not an electrician. I am not good with electrical stuff. I am very fuzzy on the difference between watts, watt hours, amps, volts, etc. So take everything that I say with a grain of salt, and if you guys have some constructive input on any of this sort of stuff, put that down in the comments below. It is much appreciated. Okay, so with that being said, this second graph makes a lot more sense to me. So here we have the old panel. Now, nothing was hooked up to the old panel. It was literally just the solar panel powering the battery. And it was like that for months. So we can see here, we've got yellow. The yellow is time in float, and the blue is time in bulk. Now, float is when the battery's just being topped off, as in the battery's full and the solar's just basically giving it enough power every so often to top it off, with the rest of the power going, who knows, elsewhere. Time in bulk is when the battery is being fully charged by the solar panel. Okay, so now, you got a couple days in here where we had a lot of time in bulk. This is because we had the battery disconnected, we made some changes, and then we plugged everything back up, but then it stabilized. And here you can see that the time in float is actually pretty decent. So it's more than 50% of the time on any given day, with a couple of exceptions, we are in float. So the total amount of time that the solar panels are powering into the charge controller, more than 50% of the time, it is being used in float mode, or meaning that there's excess power. So now let's look at the past 30-day history. So again, these two dates right here, the first two, this is when we made the change over to the new solar panel setup, and then everything from here on out has been different days, with some sunny days, some overcast days. The days where the yellow line is very long, like this one where the yellow line is 75% of the day, that was a very sunny day, okay? And then the days where it's 50%, like this one, just less than 50%, that means that it was kind of an overcast day. So what I see here, and the way that I interpret this graph, is that we've got plenty of power for the 1 nanostation that solar panel is currently powering, even on overcast days. So what I'm going to do next is I'm going to take a G3 camera, and we're going to use the 24 volt PoE pass-through on the nanostation to power up that camera in addition to the nanostation itself, and then we'll wait a couple weeks and we'll take a look at this graph again to see how things have changed. So after adding the UVC G3 camera to the solar setup, the system stayed online and the camera was powered up 24 hours a day for about 8 days. And after that point, the battery was just draining too much, and it got to the point where the MPPT charge controller had to shut off the load once the battery drops below a certain voltage. Now, after everything stabilized, it seems that this setup in this location can keep this camera and this nanostation up and running for about 14 to 16 hours per day, with about 8 to 10 hours worth of downtime starting in the very early morning. Usually it goes offline at about 5 or 6 a.m. and it comes back online in the early evening or late afternoon, right around between 4 to 6 p.m. So now let's take a closer look at the statistics that I got off of the MPPT charge controller. Okay, so here we have another look at the statistics. You can see here we have our yield versus consumption. Now, one thing that was pretty interesting is when I added the camera to the setup, the yield from the solar panel went way high. So I basically maxed out the yield that I could get from that 100-watt solar panel, whereas before with just the nanostation, it was filling up the battery, and then a lot of the power that was generated from that panel was just being wasted. It was going into la la land. But with the camera added, we maxed out the yield of the panel, and so the actual amount of sunlight and the minutes of sunlight per day that panel received made a big difference. So you can see here that the consumption, the red line, was right around 150 watt hours per day. That's what it costs to have both the camera and the NanoStation on the solar setup. What we want to see here is the blue line always above the red line. And we could see that it was very close, but then some days where it just wasn't as sunny, the yield of the solar panel dropped down so far that it was just draining off the battery. And when the battery drops below a certain voltage, it turns off the load. So then we turn off the load, everything's off for 6, 8, 10 hours until the battery charges up enough so that the charge controller can turn the load back on again. And that's what we're seeing here, is just the yield just was not able to keep up with the consumption. Keep in mind that down here the consumption went down pretty drastically because the load was turned off for significant chunks of the day. Okay, so then we have our second graph over here, and this is the percentage per charge state. Basically meaning how much time is the charge controller spending in each of its different 3 modes: float, absorption, and bulk. Bulk means all power is being shifted into the battery. Float means the battery's full and it's just keeping the battery topped off. And then absorption means, I'm not exactly sure what it means. So absorption happens when the battery hits a certain voltage. And so I think what it means, and please correct me if I'm wrong, if you guys understand what this mode means on the MPPT charge controller, I'd be really happy to hear and explain I'm 5 version of this. But as I understand it, absorption happens when the battery goes above a certain voltage level. So it's still filling the battery as much as possible, but it's keeping a more even voltage level. It's not just throwing everything into the battery, it's sort of conditioning the power a little bit differently in order to charge the battery so that it doesn't overcharge the battery accidentally. So what you see here, the yellow is float. Now, this first part here where you see a ton of yellow, this is when it just had the NanoStation. Then we move into adding the camera, and we can see that the amount of the blue, the bulk, when we're just blasting the battery with as much juice as possible, and the red, which is the absorption, that starts to go up and the yellow disappears. So what that means is that yellow being gone means that we're never at a state where the battery is completely full and the solar panel is just topping things off as necessary. And the more blue, the worse, right? Because that means that the battery voltage is just really, really low. And that's going to happen on days when you don't get a ton of sunlight. So here's another way that we can look at that same data. So as opposed to a 100% percentage per charge state, let's look at it as minutes of solar per day. So here's the same statistics, but based on the amount of minutes of sunlight, the amount of minutes of charge this was actually getting. And keep in mind that the minutes aren't exactly equal either. 1 minute of partial sunlight is going to be delivering a lot less wattage than 1 minute of full sunlight. Okay, so this doesn't really tell you how much wattage was actually happening, but you can see a distinct change here where we've got a lot of time in float, and then right around here is where I switched the camera on, and then the amount of time just went down and down. Okay, so as we move into fall and winter, the amount of downtime that this system is getting is just going to increase, right? As the sun goes further down on the horizon and as we have a lot of inclement weather, lots of rainy days, lots of overcast days, this is just not going to be powerful enough to keep this camera on probably for more than a third of the day or so. Now that actually may be okay in some places where you get a lot more sunlight. Brandon, for instance, lives in New Mexico and he gets somewhere between 14 to 16 hours of full, direct, unobstructed sunlight per day. That's probably plenty to keep everything up and running, but it's just not realistic to achieve that out here on the Oregon coast. I feel like if I doubled the solar panel to 200 watts and then added a second battery in parallel, I might be able to keep it up 24 hours a day, but I'm not going to try that with this setup. I've done enough experimenting for now, and I have a pretty good feel for the capabilities of this system. So for now, I'm just going to disconnect the UVC G3 camera, and this solar panel setup should be enough to keep the NanoStation powered all throughout the winter, but again, I'm going to keep a close eye on that, and I'm going to run more experiments as well. But that's going to be enough for this video, and just a friendly reminder that I'm going to put a full diagram of all of the wiring that I did here and the entire parts list list in a link down in the description below. So if you guys are interested in building a similar setup, I'd be curious to hear your experience with it and what type of equipment you were able to power for what periods of time. So leave your questions and suggestions down in the comments below. I hope you guys enjoyed this video. We put a lot of work into it. If you enjoyed the video, please give us a thumbs up. And if you'd like to see more videos like this, please click subscribe. My name's Chris with Crosstalk Solutions, and thank you so much for watching.